We need to understand when we're talking about heat that heat it doesn't stick around in any one place for very long. Heat transfers at typically a pretty rapid rate in a couple of different methods, one of which is called conduction. Now, conduction we can understand using the kinetic theory or the kinetic theory of matter. Just the idea that all matter is made up of little tiny pieces, and those pieces are constantly moving. So here we have some grouping of matter, and each of these little circle or oval things we can think of as being an atom or a molecule, some little tiny groups. And they're all vibrating in place. They're all moving around a little bit here. And so if we think of these as being a solid, then they don't move very much. They pretty much just stay in place, but they do a little wiggling in place. If they're a liquid, then they can kind of flow past each other. They don't have such a strong connection with each other that they can't move around a little bit. And if they're a gas, they just move all over the place. They're going crazy until they hit the wall of whatever container they're in. Then they bounce off that wall, and they might bounce off of each other. But even if they bounce off each other, they're moving too fast. They can't catch. They don't stick to each other then. So those ones are pretty well independent. But in any one of these situations, we can think of conduction as being energy that's transferred due to collisions. So if, say, we have on the left side here, we have a bunch of really hot atoms, and I'll show that as red. What does it mean to have hot atoms? Well, basically it means that they're moving fast. They're doing a lot of jiggling. So we might have motion around like this and all different directions. Oops, can't have two different directions for the same one. All different directions. And I'm showing them mostly going to the right here just so we can see how that transfers, but there'd be some going to the left and some going up and some going down and so on like that. And then on the right side, what if we have some cold atoms way over here? Very cold atoms. We'll make them blue. And they're moving as well, but just a little tiny bit. Little tiny velocity vectors. So they don't move very much. They vibrate, but the motion is really subdued here. So what's going to happen over time? And then, the middle section here, we've got probably lukewarm stuff, so a little bit of motion in there. Well, the stuff on the left side, these atoms that are moving really fast, you can see that some of these are going to have collisions with some of the stuff that's next to them, with the atoms that are next to them. So right here we've got a collision. When that happens, this one is going to get propelled off in this direction. So it was, to begin with, not moving real fast, but suddenly it's been hit really hard by this fast-moving hot atom, or atom that's got a lot of heat energy, kinetic energy, just on a very small scale. Now that one is going to be moving very quickly. This orange one is going to be moving very quickly, and it's going to collide with some atom next door to it. And we'll have some additional energy transfer there. And so we have another collision, and now this one might move in this direction and cause a collision over here. And we can see that energy, as these things move, that energy is just going to transfer over all the way through. And it doesn't have to go straight in a line like this. We might have something like this that hits up like this, and then it goes off this direction. It doesn't have to make it all the way to the right side. These things are random. They go in all different directions, but that includes the direction to the right. Well, the net effect of this is that these really fast-moving hot atoms, they've lost some of that kinetic energy through these collisions. They slowed down, and the ones next to them have sped up. They've gained some energy there. And as those collisions continue, that pattern continues until eventually these atoms on the far right side, they're getting some of that energy that started out way over on the far left side. Now, anytime we have a difference in temperatures, from hot over here to cold over here, we're going to have a net flow of energy from hot to cold. And that's how a lot of people define heat, is just a flow of energy from hot things to cold things, or warmer things to cooler things. Now, eventually we'll get to a state where all the energy, the extra energy that started out here, it's going to be evenly distributed. Now, if we distribute too much energy, we get the right side a little bit warmer, that energy is going to start flowing back this way, because then this side will be hot, and this side will be cold. The net flow will be to the left. What happens in the long term is, thermal equilibrium. This idea that the kinetic energy is spread out evenly, so we're not going to have a net flow to the right or to the left or up or down. The flow of energy to the right is exactly matched by the flow of energy to the left, and the same for up and down. Now, what happens, or what factors influence how rapidly that happens? That's what we're looking at when we talk about the rate of heat transfer. Well, you can get some ideas from this from the picture. First off, if these things are all really packed in together tightly like these ones, there are going to be more collisions. And so that energy is going to transfer more rapidly. So in general, the density of the material has an impact. And that's why you can stick your hands in the oven to pick up some food that you have in there. You can just put your hands, you probably have oven mitts on, but your arms are exposed to the hot air in there that's at 350 degrees Fahrenheit or 400 degrees Fahrenheit, and you don't get burned. You can feel that it's warm in there, but you don't get burned. But if you try and do this without oven mitts, and you pick up that metal pan inside there, it's also at 350 or 400 degrees Fahrenheit. It's the same temperature as the air, but that's going to burn you like crazy because the metal is really, really dense. And that makes the metal a good conductor of heat. And so that heat energy in that metal, it transfers into your skin really quickly. We don't feel the temperature of the thing we're touching. We feel the temperature of our skin. And so when you get burned, when something feels really hot, it's not the thing that feels really hot, it's your skin that feels really hot. So the air inside the oven, we feel some warmth from that. We have some heat energy going into our hands, but not nearly as rapidly, not nearly as much energy in that time period as we would get if we grabbed onto the metal pan or brushed against the side of the oven as we're trying to get something out. So the density of these materials has an impact, as well as the forces between these. If they're really strongly interacting, then we can have rapidly moving heat energy here. The other thing that will make a difference on these is, the size of this, the cross section of this material. So over here, if we had a whole bunch more atoms that were moving around really rapidly, then there's more collisions going to take place. So that that heat energy, that transfer is going to be more rapid. And then the other big thing here that matters is the temperature over here and the temperature over here. It turns out the bigger the difference in temperature between the warm side and the cold side, the faster that energy transfers on average. And then the last thing that matters is the distance between those two. So right now there's somebody cooking in their oven somewhere in the world, and inside that oven it's 400 degrees Fahrenheit, and I'm sitting at my desk in my chair and my body is at about 98.6 degrees Fahrenheit. Now that's a really hot oven and a really hot me, but there's a really big distance between the two of us. So the net flow of energy from the oven to me is really, really slow. So slow it's essentially zero. So if we combine all these, we can get an equation and a representation of how heat flows. So I'm picturing this as just a slab of some material, say some rectangular prism of metal or whatever it is, and then that material has some cross-sectional area A. We've got a warmer side and a colder side with temperature 1 and temperature 2 here. K represents the thermal conductivity of the substance, so those factors that influence how rapidly heat flows within the material itself. So the density is a big one here, and then L for the length of the distance between the warm side and the cold side. And then the equation we get for the rate of heat transfer is right here. It's K, the thermal conductivity, times the cross-sectional area, times the difference in temperatures divided by the L, the distance between the hot side and the cold side. And then H is the rate at which heat flows. So the units for H would be, that'd be joules per second. So how many joules of heat energy transfer for each second that goes by.